Greetings and welcome to the Chemistry 223 lecture for Chapter 19, which covers the chemistry of coordination compounds. Coordination compounds is something that's kind of near and dear to my heart. My background is in inorganic chemistry, which is a chemistry of metals and how they react. And a lot of the coordination compounds were types of compounds that I looked at in my graduate work especially. So I like talking about coordination compounds. I think they're kind of cool. There's a couple of things I really do want you to hear in this section, and the notes here and this video for chapter 19 is going to show you like the minimum part and stuff that you need to know for, say, the final exam or for the take-home quiz, stuff like that. If depending on how much time I have in lecture, I might be able to cover a little bit extra beyond this material, but at least this video will show you the important part, so you'll be good to go for the rest of the class. Okay, without further ado, let's check out chapter 19. Color is something that's really been important for me, and you may not have thought about color that deeply or anything like that, which is totally fine, but maybe you're curious, like, where does the color of objects come from? Like, why are some things blue and why are some things red, etc., etc.? Well, most of the time it's from the paint covering the object, all right? It's usually a type of a coating that gives it its color, all right? Sometimes some substances do have an innate color, but often it's from the paint. Well, where does the paint get its color? Great question. Where does the paint get its color? And if you've ever been to a place like Miller Paint or one of these kind of places, man, they have a lot of colors. So there must be some way to get all these different hues. The paint colors come from the paint pigments, which are parts of the paint. And the good paint people can mix the right pigments to get any kind of shade and stuff like that that you might want to. Well, you know what's coming next. What are the pigments? What are they exactly? Great question. Those are basically colorful transition metal compounds. And the transition metals, especially the ones that are ionic, have just an incredible array of different colors. And this little picture here in the lower left shows some of the colors. Now, it's basically just a series of metals there you're seeing: chromium, manganese, iron, iron plus 2, iron plus 3, cobalt, nickel, copper, zinc. But you can see how as you change them with what's around them, the colors change. So the upper left there is the original aqueous ion, so what it looks like in water. And then the next one down is an aqueous sodium hydroxide, and the next one's ammonia, and they go on and on. So there's a lot of colorful compounds that come from transition metals, which is really cool. In organic chemistry, they say that if you're lucky, your compounds will be white or maybe black, and if you're unlucky, brown. So basically in organic chemistry, most of the things are white if you're lucky, maybe black if you're lucky enough, and then brown is usually what happens when something has oxidized, when it turns bad. So in transition metals and inorganic chemistry, whoa, we have a whole bunch of different compounds to choose from. So let's explore the chemistry of these transition metals a little deeper. Transition metals are found in nature all over the place. They're in rocks and minerals. Things like rubies and sapphires have different types of transition metals. They're also found, though, transition metals are also found in a lot of biomolecules. So, for example, vitamin B12, which is really important, has cobalt. Hemoglobin has iron. Cytochrome C is another one with iron in it. So there's lots of places that transition metals pop up in our world that we may not think about. In industry, transition metals are used a lot. Steel is a mixture essentially of iron and carbon, and a lot of the alloys that are used in industry basically have different types of transition metals. The pigments that are used a lot of time are all over the place, but some of the more common ones, one of them is quote-unquote titanium dioxide, quote-unquote, and I hate that name. It really should be titanium four-oxide, but that's my own personal problem. Anyway, TiO2 is a white color, lead-2 chromate, PbCrO4, is a yellow color, and that Fe4 FeCN63 thing, that's called Prussian blue, and it is a really beautiful blue if you've ever seen that particular transition compound. On the periodic table, the main group metals are the A groups, and the kind of tan groups, the two on the left hand, the two columns on the left hand side, and the 6 columns on the right hand side, those are the traditional main group metals. Now in this section, what we're going to talk about is mostly the transition metals, and the D block, especially the upper ones, those are the transition metals. We'll also throw in some of the F block, what they call F block transition metals. The top group of those are called lanthanides, and the bottom group are called actinides. But their chemistry is actually a little bit different than the main groups. In this picture, we're seeing the 3D, the 4D, and the 5D transition metals. And these are the ones that we'll focus on mostly in this section. We won't talk as much about the lanthanides and actinides, the F block. There's also a 6D group under this group now. Those are mostly radioactive with really short half-lives, so people haven't studied them as much. These are the ones we'll mostly talk about. Anyway, it says they most have partially occupied D subshells in common oxidation states. Now, oxidation states is just a fancy way to say a metal with a charge. All metals like to lose electrons, but if you remember, with all of the transition metals, they will lose the beginning S electrons first before they lose the D electrons. So for example, for scandium has an argon core. It's a 4s2 3d1. And if it becomes a positive 2 scandium, it's not the 3d electron that comes out first, it's actually the 4s. In Chem 221, we talked about how higher n orbitals, electrons, come out first, and that 4 of the 4s means n equals 4. And that's a bigger number than this number, which is the n number, n equals 3 for 3d. So most of these transition metals, when they have a charge, they'll mostly have some d electrons running around, okay? And it's a lot of the d electrons that results in the colors that we've seen so far, and we'll see more of in a little bit. So transition metals are very metallic. Big surprise, they're metals, right? Metals love to be bent, malleable, and stuff like that without breaking, which is kind of cool. They're not as reactive as the alkali and alkaline earth metals. Those metals are really anxious to get rid of their electrons. Transition metals want to get rid of their electrons too, but not quite as quickly. Transition metals, though, do have high melting points and high boiling points, and the densities of some of the transition metals are the highest of all. Osmium and iridium are the two highest density elements on the periodic table. They're always fighting for which one is the most dense. Transition metals have 1 or 2 s electrons in the valence shell, so that means that they have like 4s filled in before 3d in the case of the 3d transition metals. Now, there are some exceptions to the n plus L rule. So for example, chromium does not have a 4s2 3d4 configuration. It's a 4s1 3d5. This is something we talked about in Chem 221 as well. So that one would only have 1 s electron instead of 2. The s electrons, whatever they are removed first when you're making positive ions of the transition metals. The different number of d electrons is important, and the number that goes in front of the d is n minus 1. So on the earlier example with scandium, it was argon 4s2 3d1. The d electrons, you always go n minus 1. So the 3d electrons, the 3d transition metals, are in the fourth period. So n is the 4, the period number. So to figure out the number that goes in D, you go 4 minus 1 or 3. And so below it, which are the fifth period, you would go 5 minus 1. Those would be 4D. So for example, rhodium is a 4D element. Unlike the main group metals, which mostly have a fixed charge, most of the transition metals have variable oxidation states, and that just means they have variable charges. And this is why we started using the Roman numerals back in Chem 221. If I said, hey, go get me some iron chloride, for example, you would see FeCl2 and FeCl3, and one extra atom can make a big difference in reactivity, so that's why we called them iron 2 chloride for FeCl2 and iron 3 chloride for FeCl3, stuff like that. Paramagnetic and diamagnetic ions exist when you start making positive charges on transition metals. And this is something we'll look at more a little bit later. Paramagnetic atoms are attracted to magnetic fields or sometimes repulsed. Diamagnetic atoms could care less about magnetic fields. So paramagnetism usually means more reactive. And most of the ions are deeply colored. And there's something called crystal field theory. And if I had unlimited time, time in Chemistry 223, this would be the first thing I would add back in. Crystal field theory is kind of like valence bond theory in Chem 222. It's a way that chemists can make sense of a lot of the transition metal behavior using the idea that these little tiny atoms and electrons are in like a field, and it's a cool thing. Crystal field theory is also in competition sometimes with molecular orbital theory, but like we saw in Chem 222, molecular orbital theory is very complicated. It was very complicated in Chem 222, so we only looked at simple examples. If you start adding in d electrons and transition metals, trust me, it gets even more complicated. So crystal field theory is a little bit easier to approach theory, then there's a lot of things you can do with it. But alas, we probably won't have time in this class, but maybe one day. Here's some electron configurations just to kind of remind us here of what's going on. I'm using here the noble gas notation. So I'm using argon in brackets, and argon in brackets means 1s2, 2s2, 2p6, 3s2, 3p6. Now, after that, 4s2 are the next electrons to be added, and then 3d1. So if you list the configuration as argon, 4s2, 3d1, that's totally fine. That would be the electron filling order. But sometimes we're going to see it's better to write them with the 4s electrons last, because the 4s electrons have a higher n. The number in front of the letter there, S or D, is the n number, and higher n electrons come out first. So the 4s electrons always come out before the 3d. Scantium 3d1 4s2, titanium, argon 3d2 4s2, vanadium 4s2 3d3, or 3d3 4s2. Now you would expect chromium to be, which is the next one after vanadium, to be argon 3d4 4s2. But chromium is one of the exceptions, and for reasons which aren't understood, at least through understanding the n plus L rule, which is what we use to figure these out, one of the electrons in the s orbitals jumps ship to the 3d set. So chromium has an argon 3d5 4s1 configuration. Then when you go to manganese and the other ones, they go back to normal. It's no big deal. Copper is another exception. Copper you'd think would be 3d9 4s2, but in reality it's 3d10 4s1. And then finally zinc, argon 3d10 4s2. Here's a question. What's the electronic configuration for neutral cobalt? Okay. Now, cobalt is an atom. It's a transition metal. It's one of the 3d electrons. And if you have a periodic table, this question would be a lot easier, definitely. Cobalt has, if you look on the periodic table, it's a 3d7. Now, 3d7 comes from literally counting the atoms starting at scantium. Scantium, like you see there, is 3d1. Titanium right next to it, 3d2. After that is vanadium, 3d3. Then chromium, 3d4. Manganese, 3d5. Iron, 3d6. Cobalt, the next one, 3d7. So notice that I didn't do anything fancy here. I literally started counting at scantium, which is the 3d1, and I just kept going. And each extra atom adds one more to the 3d core. So cobalt has a 3d7 4s2 or 4s2 3d7. Remember that argon is a total of 18 electrons. So 18 electrons plus 7 plus 2. I'm hoping that's 27 electrons total. 27 is the atomic number for cobalt, so it should have 27 protons, and the neutral atom 27 electrons. Here are some likely charges on some of the transition metals. And notice first of all right away that most of these have more than one charge on them. And just because the charge isn't listed doesn't necessarily mean that the charge isn't available to you. So for example, scantium over there only lists a positive 3, and that is the most common, but you can have a positive 2, for example. It's rare, but it does go down. A lot of these, as you can see, like manganese and iron, wow, they have a lot of charges, and chromium for that matter too. And this is why we use the transition metals. We use the Roman numerals for them, because it's hard to say if you have manganese +2 or manganese +5, or iron +6 or iron +3, etc., etc. Now, zinc was one of the stairs we talked about. Zinc is always +2, and that's a pretty good bet because, as you can see, zinc basically is just +2, all right? It's one of the few transition metals that have a predictable charge. If you put Roman numerals by zinc for its charge, I would not be disappointed, but it's okay. Now, last thing, there says there's loss of ns electrons. There's usually 2 s electrons before the 3d. So like as we talked about, scantium is 4s2 3d1. If the atom loses 2 electrons, those 2 electrons will come from the ns shell. So scantium +2 would lose its 4s electrons first, and it would have a 3d1 electron configuration. Once you go past +2, though, that's when you start losing the d electrons. So if scantium has lost a 3rd electron, that 3rd electron will be the 3d electron. They'll all start going down. So the first 2 electrons out are the ns, and the remaining electrons out are n-1d. So for scantium, that would be 4s electrons first, and then 3d after that, etc., etc. How many d electrons does the cobalt 3+ ion possess? Now this is kind of cool. So we saw just a little bit ago that cobalt is a 4s2 3d7 atom when it's neutral, okay? And cobalt +3 means that we're taking away 3 electrons. Well, if you have a 4s2 3d7, it might be tempting to take all 3 electrons from the 3d, so there would be 4 d electrons left. But remember, highest n electrons come out first. And so for cobalt here, that means the 4s2 electrons would come out first. Then the last electron, because we're taking away 3 to make +3, that last electron is going to come from the 7. We would expect cobalt +3 to have 6d electrons, all right? The first 2 electrons are always the ns electrons, the 4s, and after that is when you start losing the d electrons. So cobalt had a 3d7. Only one of those was taken out because the other 2 were the 4s electrons. Here's some more examples of electron configurations. This is iron losing 2 electrons to become iron 2+. An iron neutral would have an argon 3d6 4s2. As you remove 2 electrons, remember, take them away from the 4s first. Our iron +2 would be argon 3d6. Hopefully you can see now why we're listing these as 3d6 4s2 instead of 4s2 3d6. The 4s's are the first ones out. They're the first ones in and the first ones out. It's kind of weird. Most of the atoms aren't that way, but most of the electrons in atoms aren't that way, but for these kind it is. If you make iron +3, then you'll start losing the d electrons. So at this point, you do lose d electrons. Iron +3 would have a 3d5. If you made iron +6, if you lost 3 more electrons, they would all come from the 3d set as well. Iron +6 we would expect would be 3d2. So you always remove the valence, the outermost ns electrons first, and then you start losing those d electrons, the n-1 d electrons. Now, we talked earlier about paramagnetic and diamagnetic. Paramagnetic species are usually more reactive. They're attracted or repelled by magnetic fields. Diamagnetic things aren't quite as interested in magnetic fields. Now, paramagnetism does depend to a point on how many unpaired electrons you have. So if you have a lot of unpaired electrons, it's really paramagnetic. And if you don't have that many unpaired electrons, it's not as paramagnetic. In all fairness, there's lots of caveats to all this, but at least it gives you an idea of what people think about when they think about paramagnetism. Here's an example of chromium. Now, chromium is an argon 3d5 4s1. This is one of the exceptions to the n+L rule. We think it should be 3d4 4s2, but for whatever reason, it jumped ship. I bring this out because chromium has 6 unpaired electrons, 6 arrows pointing up without a down, and each one of those electrons is paramagnetic. So chromium is very paramagnetic. On the other hand, palladium, which is another one of the exceptions, palladium, which is one of the lower rows, has a 4d10 configuration with no 5s electrons. In palladium's case, every up has a down electron. Palladium is diamagnetic. Palladium is not very interested in magnetic fields, but oh man, chromium sure is, because it has 6 unpaired electrons, 6 possible ways to be attracted. So this leads us into coordination chemistry. And coordination chemistry really boils down to a Lewis acid center and Lewis bases outside of it. And in this section, our Lewis acids will always be transition metals. Transition metals make great Lewis acids like we've seen in previous sections this quarter. And if you have a Lewis acid with Lewis bases around it, it ends up making a complex ion. And sometimes it's just abbreviated complexes, all right? These complex ions, as we've seen, can be super stable and easy to form. In this world, a Lewis base is oftentimes referred to as a ligand. So in the first example equation right there, we've got an iron plus 3, that's our Lewis acid, and 6 cyanides. And cyanide has lone pairs on both the carbon and the nitrogen if you draw out the Lewis structure. Anyway, that's a great Lewis base. So it's going to make a complex ion where the iron's in the middle and the 6 cyanides are all around it. Notice the charges. Iron started as +3, each cyanide is -1, and there's 6 of them, so -6 plus 3, overall complex ion there has a -3 charge. The next example is a nickel ion, nickel plus 2, and it's another great Lewis acid. It's going to be surrounded here by ammonia, NH3. Remember, ammonia has a lone pair on the nitrogen. So 6 ammonias can go around the nickel. The charge +2 on the nickel goes to the complex ion because ammonia is neutral. These are the ways then you can start thinking about complex ions. So complex ions in this world, or complexes, are really nothing more than Lewis acids, a transition metal, in the middle of these ligands, which are like Lewis bases. We'll see some weird ligands that we're not used to, but that's really all it comes down to. They'll always have multiple ligands or multiple places that you can connect the transition metal to. Kind of cool. So again, the Lewis acid is the metal. That's going to be where everything gets coordinated to. And the Lewis base, which has the fancy name ligand, that's where the lone pairs are going to connect to the Lewis acid. They're going to donate their electrons. And this creates then these molecules or ions. They're covalently bonded, sharing. It's a coordinate covalent bond usually, but that's cool. These things are actually pretty stable. A coordination compound has one or more complexes. Now, a complex ion is something we've seen already, and it's something with a charge. If you can make that coordination or that complex ion a neutral species, it becomes a coordination compound. So if you look at some of these examples, like let's look at this one right here. CONH36Cl3. Well, that's a cobalt, and we're going to see that a lot of times they'll have 6 pieces around them in an octahedral fashion. So the part in brackets is the complex ion, and we coordinate 3 chlorides around it to make it neutral. So that's an example of a coordination compound. The second one has 2 complex ions. This is a copper with 4 ammonias around it, and this is a platinum with 4 chlorides around it. The first square brackets with the copper, that's the positive cation. The second square brackets with the platinum, that's the negative anion. But they come together in 1-to-1. The whole thing is neutral. It's a coordination compound. And the next one is the same thing as well. The coordination number is something that people talk about in coordination chemistry, and that's literally just the number of donor atoms bonded to that central Lewis acid metal atom, all right? And coordination number is usually no smaller than 2, but it can be 6 and even bigger sometimes depending on the metal. So in the cobalt example with 6 ammonias around it, well, there are 6 ammonias, 6 sites of coordination, so the coordination number would be 6. The PTCl4 thing actually has a -2 charge, but that's not important here. That platinum has 4 ligands around it, 4 Lewis base chlorides, so the coordination number is going to be 4. Most common definitely are 6, 4, sometimes 2. You can have different numbers. You can have bigger than 6, especially with lanthanides and actinides. But most of the time for transition metals, 6 and 4 are very common, and sometimes 2. If you have a coordination number of 2, then the pieces that connect to the central atom, like with Lewis structures in Chem 222, usually want to be as far apart from each other as they can. So if you have a coordination number of 2, the geometry is almost inevitably linear. And that's a very similar thing to problems like Lewis structures with carbon dioxide. We saw the 2 oxygens wanted to be as far apart from each other as they can. And that's the same way here with these coordination complexes. AgNH3+ is a complex ion. It's great at removing sometimes silver chloride from glassware, but anyway, that would be an example of a linear geometry. The light blue atom in the center would be the silver, and then the dark blue circles on the outside, each of those represents the nitrogen in ammonia. If you have a coordination number of 4, there's 2 possible geometries, and the most common geometry usually is tetrahedral, just like in Chem 222. ZnNH342+ was a complex ion we talked about in the Le Chatelier's principal lab. That actually has a tetrahedral geometry around it. The 4 ammonias try and get as far apart from each other as they can. So is the FeCl4- thing. However, you do sometimes have square planar geometries. Square planar geometries usually happen when the transition metal has lone pairs of electrons on it. So NiCN4-2 has a square planar geometry. The light blue atom in the middle is nickel. The little red dots in the square around it, each one of those represents a cyanide. And you can imagine that above and below the screen, you would have a lone pair on the nickel. That's what gives it the square planar geometry. I would argue that a coordination number of 6 is most common, and in a coordination number of 6, you will have all the ligands in an octahedral field, and that just means all the ligands will display above, below, left, right, forward, backwards kind of things. These are very, very common. So COCN6-3, that weird FeEN3+ thing, which we'll talk about in a little bit, that's octahedral. Octahedral is very common when it comes to transition metals. The charge on the complex ion is going to be found by just taking the individual charges on the metal and the ligands, and you can find out what it is. On the other hand, the charge of a compound, you have to think about cations and anions separately in order to figure out what's going on. On the left is FeCN6-3. That's a complex ion, okay? So if we were curious what the charge was on the iron, we have to go back and remember that cyanide, Cn is a -1, and there's 6 of them, so the cyanides give a total of -6. But the overall molecule has a -3 charge, so something is giving up a +3 to balance that, and that's going to be the iron. So this is an iron +3 center, because +3 - 6 gives you the charge on the complex ion, that -3. I would refer to this as an anionic complex ion. It has a negative charge, so it's an anion, and it's a complex ion. It has a charge. No problem. On the right-hand side, we have a compound, a coordination compound. But if you look carefully, there's a part in square brackets, and there's chlorides on the outside. The parts in square brackets, that's a complex ion. And so what we'll do is we'll figure out what the charge is on the cobalt first, and then figure out what the rest of it is later. Now, NH3 is ammonia, and ammonia is a neutral ligand, so ammonia has no charge. But the cobalt there is being balanced on the outside by 2 chlorides. And since Chem 221, chloride has always been -1, and there's 2 of them, that must be a cobalt +2 center. So in this neutral compound, the +2 cobalt is being balanced by 2 -1 chlorides. The CONH36 thing, that's a complex ion with an overall +2 charge. However, if you complex it with 2 -1 ions, you end up making a compound. So complex ions have a charge, compounds are neutral. Here's a molecule, CuNH32Cl2, and it says what's the charge on the copper. no problem. Ammonia, NH3, is neutral, so we don't have to worry about that. But you do see that there's 2 chlorides and 1 copper. So chloride, like everywhere, has a -1 charge, and there's 2 of them. Copper is balancing that out. Notice that there's no charge on that molecule. It's a neutral compound, so this must be a copper +2, all right? And again, having all these ions in your brain really helps out. Ammonia is neutral, chloride's -1, all is well. So these ligands, which are really just Lewis bases when it comes right down to it, they're basically just these things with lone pair electrons on them. And the lone pairs push themselves into the empty orbitals on the Lewis acid, making these kind of connections. Now, in coordination chemistry, they talk about dentate. And dentate apparently is a Latin phrase that basically means tooth. And you can talk about the number of teeth on a ligand. So as an example, a lot of the things we've seen so far have been monodentate, which means they have 1 tooth or 1 set of lone pairs to attack a metal atom. But we're going to see here in a little bit that you also have bidentate ligands, which means they have 2 places they can connect to a metal center. We're going to look at tetradentate ligands, where they have 4 places to connect to the metal. And we'll even look at some hexadentate ligands, 6 places to connect to a metal atom. If you don't know how many connections there are, you can call it polydentate. That just means 2 or more donor atoms. And sometimes they refer to these as chelating agents. I can never say that word, sorry. A chelating agent is just a polydentate ligand that can be used to surround a metal and sometimes pull it out of solution and stuff like that. Monodentate ligands are very common, and we've seen quite a few of these already in our chemistry classes. Water is a great monodentate ligand, all right? It's small, relatively. It's got good lone pairs on it, so it connects well to the metals. And I would argue that any metal atom in water has water's complexed around it. In this picture, it's kind of hard to see, but at the very bottom, it says CuH2O6 2+. So in the lower part there, that's a water complex of copper. The copper ions have 6 waters around them in an octahedral kind of situation. They're almost always around if you have them. This is the ion dipole force we talked about in Chem 222 and the intermolecular forces. It's pretty strong about getting the metal ions in water, at least usually. So if you do get the metal ion in water, it's usually because the water's around it. Now there's lots of monodentates, all right? We've already seen examples of cyanide, Cn-, ammonia, NH3. You can have nitrites, NO2, thiocianides, SCN, hydroxides. You can have the different halides. CO is actually a possibility, a carbon monoxide. We'll talk about that in a little bit. Even oxide once in a while is a monodentate ligand. So we've seen lots of examples of these already, but here's some more. Here's a cobalt with 6 monodentate ammonias around it. So you know that that's octahedral. The next one has 6 thiocianides around the iron. So that's also octahedral. And again, notice how the charge changes. Both of those are metals with +3 charges, but ammonia is neutral. So the +3 soars on out. On the other hand, thiocyanide has a -1 charge. There's 6 of them, so they cancel out the +3 and end up with a net -3 charge. A bidentate ligand is just a Lewis base, but with 2 places to connect to the metal center, or 2 teeth, all right? And that's kind of interesting. And some of the common examples of bidentate ligands in coordination chemistry include the oxalate ion, which we've talked about a little bit in this class, but not a lot. Oxalate is just a big polyatomic ion. A much more common bidentate ligand is the ethylene diamine ligand. Ethylene diamine, so diamine, 2 amines, and if you remember from organic chemistry, an amine is a nitrogen-containing compound. Ethylene is kind of a common name for ethene or an ethane. It's 2 carbons, all right? So ethylene diamine has a 2-carbon center, and on each carbon you have 1 nitrogen, 1 amine group. That's what it is. Now, for this particular lecture, the nitrogens each have a lone pair. And so each of those lone pairs can be used to attack a metal center or attach itself to a metal center. So that's why they call ethylene ethylene diamine, a bidentate. And then there's also the massive orthophenanthroline, which people abbreviate OPHEN. I'll show you a picture of that in a little bit. That's a pretty big molecule. Notice that ethylene diamine is oftentimes abbreviated EN. All right, we saw an EN earlier and I kind of brushed it off. Now you know what EN means, ethylene diamine. So if you have a complex with a bidentate ligand, and assuming the complex is octahedral, you will see fewer ligands. So like COEN33+, that has 3 bidentate ligands around it, and each of those has 2 teeth. So that would be a total of 6 connection points. That's going to be octahedral. The same thing for the chromium oxalate there in the next line. 3 bidentate oxalates can surround the chromium. And the last one is also octahedral too. It has 4 ammonias and only 1 O-phenanthroline molecule. That's a bidentate. Orthophenanthroline is a really big molecule. Here's the molecules written out more like a Lewis structure. So at the top is oxalate. It's a carbon-carbon backbone, and there's double and single bonds, and those bonds will resonate. The stars represent where the -1 formal charge, if you will, is, and the -1 can resonate with a double bond, stuff like that. Ethylene diamine, the lone pairs are on the nitrogen. That's where it connects. And there's the orthophenanthroline monster. You can see that it has 2 nitrogens there on those kind of aromatic rings. That's where the molecule connects to the metal center. That's a lot bigger of a molecule, so it's harder to put more than 1 around a metal center. This is a type of display called ribbon theory, and it's used a lot in biochemistry. And instead of listing all the different atoms and stuff like that, what they'll usually do in ribbon theory is they'll have like a central atom, and then they'll have the main connector atom. So for ethylene diamine, the EN, that would be nitrogen. And then you can see there's like this kind of ribbon right here, and that's just all the carbons and hydrogens and stuff like that, and pieces honestly that aren't as important. The advantage of ribbon theory is that you can definitely see the geometry around the atom in question. And when these molecules get big, that can be really helpful. On the other hand, when you're learning things, it's hard to remember that, boy, each one of those nitrogens has 2 hydrogens and a connection to carbon, etc., etc. So there's advantages and disadvantages, but you will see it more and more in biochemistry, which is kind of cool. Again, ethylene diamine is a neutral molecule like ammonia, so it doesn't affect the charge. Cobalt +3 can put 3 ethylene diamines around it and still be +3. Here's an example of where someone was able to put 3 orthophenanthrolines around an iron +2 center. Now, orthophenanthroline is also a neutral molecule, all right, so it doesn't affect the charge. But the geometry of this I find very, very fascinating, and other people do too. Sometimes people will call this like a propellerane because it kind of looks like a propeller going around. There's a lot of cool kind of geometry things that's going on. In that picture, the red atom is the iron. The blues, once again, are nitrogens, and everything else is basically like carbon, and hydrogens aren't being shown. But I love the geometry. I find that kind of mesmerizing for some reason. But yes, I need to probably go out and get fresh air. One of my favorite molecules is dimethylglyoxime, and that's abbreviated DMG. If we did the QA3 lab in a face-to-face lab this quarter, when you confirmed the presence of nickel, you added dimethylglyoxime to a nickel solution, and nickel with dimethylglyoxime makes a kind of a cool red color. So nickel dimethylglyoxime 2 is actually something that you may have made. But even if you didn't make it, it's no big deal. This is also a bidentate ligand, and you can see in the picture that this dimethylglyoxime thing has again 2 nitrogens with lone pairs. Now in this molecule, you're also seeing some hydrogen bonds. That's what the OH bonds are right there. It's another way to help connect these molecules together to make it a little bit more stable. And again, this is a square planar molecule. If you look at that rotating molecule, it's actually mostly 2-dimensional, a flat molecule. Nickel has some lone pairs sticking up and below the nickel. That's why they're square planar. Kind of cool. Here's a structure for ethylene glycol. Ethylene glycol is a diol. You could also call this 1,2-ethane diol if you remember organic chemistry. Anyway, just describe the dentate character, all right? And I was laughing there because I just looked at my answer E, which is 0 dentate, which doesn't make any sense. But anyway, I crack myself up. When I crack myself up, I think it's a personal goal. But anyway, I'm digressing once again. Sorry. If we wanted to figure out how many teeth this thing could have, what you want to do is look for the number of lone pairs. And you can see that there's an OH on the left and an OH on the right. So I would argue that this is a bidentate structure. If you have a lone pair, you have at least the potential for making a connection to a metal atom. Now, the lone pairs can't be right next to each other. You have to have a couple of atoms between them just to kind of keep the distance apart and stuff like that. But I think ethylene glycol could totally be a bidentate ligand looking at that. EDTA is another example of a ligand that's used a lot, but EDTA is very wild. It's considered a polydentate ligand, which means it can have more than 2 or more, but up to even 6 different teeth connecting it to the metal atom. EDTA is really fascinating. It forms 1-to-1 complexes with most metals on the periodic table except for group 1A. And what that means is that if EDTA sees a metal, it basically attacks it, and one metal per one EDTA molecule is like the resulting complex that forms. It does not do very well though with group 1A, so don't expect it to get the sodium out of your diet or potassium or lithium or something like that. EDTA forms very stable water-soluble complexes, which is kind of nice, so you can get them into your bodies and get them out if you need to as well. EDTA has high formation constants. A formation constant is an equilibrium expression for a complex ion, and if the equilibrium constant is high, that means very product favored. EDTA combined with metals usually have very high Kf values, so they're easy to form. EDTA is considered a primary standard, and primary standard means that you can keep it literally in like a little container on the shelf and pull it down after a couple months and use it no problem. A lot of materials will take water and hold on to them, or they'll decompose. A primary standard is considered to be pretty stable and usually very it's not into water either and stuff like that. So you can use it pretty readily, which is nice. If you are a fan of bad movies, and I am almost the king of this, the Blade movie, the original Blade movie with Wesley Snipes, he actually used a EDTA solution to fight vampires. And EDTA, the idea is that EDTA would surround whatever metal the vampires have in their blood and cause them to do some crazy things. If you do happen to see the original Blade movie, please laugh with me. I really do kind of like that movie, I have to admit, but you can laugh at it with me. It's quite all right. Anyway, if you see it, all right, EDTA. EDTA looks like this. This thing is called ethylene diamine tetraacetic acid, and EDTA has up to 6 possible dentate positions, and each of those little stars up there represents one of the places where it could make a connection to a metal. And you can see that each one of those star places has a lone pair of electrons. It's ethylene diamine, so ethylene is the 2 carbons in the middle, diamine, the 2 amine groups, but it's also tetraacetic acid. Now, acetic acid would be CH3COOOH. They're not including either the lone pair or the hydrogen here. Most of the time, for most of these complexes, I would put just another lone pair right there. So this would be the deprotonated version, or the more basic version, if you will, all right? But sometimes the EDTA complexes will actually have the hydrogen there. It just depends. But what's really cool is that this molecule is so big, if it sees a metal, it literally wraps itself around the metal center. And then if it's wrapped around it, you can flush it out with water. So it's a great metal extractor. If you accidentally get metal in there, EDTA will sometimes pull the metal out. Here are just some kind of cheesy pictures showing different combinations of how EDTA works. EDTA, again, does have 6 possible positions. Now, on the left-hand side, it's hard for, I think, anybody to make sense of what's going on. That's pretty ugly. But with ribbon theory, it kind of breaks it down once again. You can see the blue nitrogens, the kind of red oxygens, and the cobalt in the middle. So it's easier, like I said, a lot of times to see the ribbon theory than it is the actual like Lewis structure form. These values are the log of the formation constant. Now, these formation constants are very product favored, which means very large. So if you take the log of the K, these are the numbers you get. And all of these are really big numbers. If you wanted to turn it back into a regular K, you take the anti-base 10 log, you'd go 10 to the power of 25.1, for example, to get what the K is for iron plus 3. So these guys really like to form very high formation constants. And again, that just tells you as a scientist that if you put EDTA in with metals, it's going to pull them out. It's going to surround the metals, pull them out of your own other complexes. Maybe that's a good thing, maybe that's a bad thing, but be careful. And it is kind of a powerful tool sometimes when you're dealing with metals. Now, there are other chelating agents besides the one we've seen, and I just want to briefly go over them. Biochemistry is filled with these chelating agents, which are basically just polydentate ligands. This one is porphine, all right? It's apparently a really popular one in nature. And again, my knowledge of biochemistry is not great here, so I apologize. But with good old-fashioned Google, I'm sure you could find all kinds of cool information. The nitrogens in the middle on the left kind of show where the connections can be made to the iron, and then in the lower right you actually have the iron connected. Myoglobin is an iron-containing protein, and it stores oxygens in cells. And again, if you have like all the atoms, you can't make heads or sense of it. But again, using that kind of ribbon theory thing, then you can actually see what's happening. So in that little part there in the middle, the little blue atom there is the iron. There's a nitrogen kind of 5-membered ring above it, and the oxygen, those 2 little O atoms, is below. And so it's able to hold on to the oxygen until it's needed, then it releases it. Good to go. Oxymyoglobin is another one of these. Again, it's iron. It holds on to the oxygen on one side and that nitrogen 5-membered ring thing on the other side. And again, in biochemistry, you'll look a lot more into this, and I'm sorry I don't know more cool facts about it and stuff, but it's kind of cool. This is kind of a stupid joke, but I had to throw it in here. You know, these stupid memes, I kind of fall for them sometimes, especially when I'm kind of bored or whatever. Anyway, I saw this. It's like hemoglobin, and hemoglobin is connected right now to oxygen, and that's good. But you can see hemoglobin is being distracted by carbon monoxide. I put this in here because carbon monoxide has a higher formation constant to the iron and hemoglobin than oxygen does. So if hemoglobin is around carbon monoxide, it'll take the CO up and kick the oxygen out. And that's bad for our bodies. Our bodies need the oxygen. CO, of course, will kill us. So anyway, stupid meme. I apologize. My poor sense of humor. This is kind of a strange lecture, you can tell. The last big thing I really want to talk about in this section is how to name coordination complexes. And we haven't talked about these so far, but if you're ever in the outside world and you see one of these names, whoa, they look intimidating. They're usually long and they've got weird symbols in them and stuff like that. So I want to have a quick introduction to how to name coordination compounds, and they're not too bad. Like all compounds we've seen in chemistry so far, it's always cation first and anion second. Cations are first, anions second, but if there's a metal in the anion, it gets an ATE ending. And I'll show examples of all of this here coming up. This is kind of the boring rules part, okay? Ligands are named first in alphabetical order, so ligands before the metals, all right? Most ligands will have an O ending, but if you have multiple ligands, you have to use Greek prefixes, di, tri, stuff like that. The metal atom or ion is is always named last, and the metals always have the Roman numeral oxidation state following them. And that's not always the case in some of the compounds we've seen, but anyway, if you do need one, it does need to be included in these coordination compounds nomenclature rules. This is the weird part. You don't want to put any spaces in the complex ion name. So some of these names can go on for a long time and they look really weird at first, but trust me, you can do this. I do have a coordination compounds handout in the companion and also online, and I encourage you to check it out. It's got some examples of how to name these things. They're not too bad. The ones we're looking at are pretty chill. And again, I just want to kind of introduce this so that if you do see them in the future, you won't be intimidated. IUPAC is the official group that creates the rules, if you will, for these different names. And neutral ligands are usually referred by their usual name, but there are some exceptions, okay? And these can be a little strange. Water, if you see it in one of these complex ion names, is referred to as aqua. You don't call it water, you call it aqua. And ammonia is really weird. If you have ammonia in one of your complex ions, you refer to it as an amine. Now I want to stop right there. Amine in this then is AMMINE. And we've already seen in organic chemistry that you can have an amine, which is when you have a nitrogen with an alkyl group R and maybe another alkyl group, another hydrogen. Those are AMINE. So an amine in organic chemistry is different than an amine in coordination compounds. In coordination compounds, you'll spell it with two M's and it means ammonia. In organic chemistry, an amine, like ethylene diamine, would be just a single nitrogen with at least a carbon on it. Okay, carbon monoxide is called carbonyl. This is another one that's strange. Carbonyl in organic chemistry was a carbon-oxygen double bond. So for example, ethers had alkyl groups on both sides of the carbonyl. That was cool. A carbonyl in this stuff is just a carbon monoxide. So it's a little bit different rules for a little bit different nomenclature system. Just think about that as we go through it. Hydroxide becomes hydroxo. That's weird, but I can dig that. Some ligand names already have a Greek prefix in them. So for example, ethylene diamine has di already in it. If you had two ethylene diamines, it would be diethylene diamine. And that sounds weird. Like, do you have two ethylenes and two amines? Or is it two ethylene diamines? So if your Greek prefix or if your ligand, already has a Greek prefix, then what you want to do is use the alternate prefixes. And these are bis, tris, tetrakis. So for example, if you do have two ethylene diamines, you don't want to call it diethylene diamine because you're not sure where the di is referred to, etc., etc. What you would do here is call it bis ethylene diamine, and bis is just an alternate form of saying two. Tetrakis is 4, hetrakis is 6, etc., etc. Let's look at some examples. These things get really weird. So let's say we wanted to name this thing. It's cobalt. It has 6 waters and a +2 charge. Water is neutral, all right, so it doesn't affect the +2. So the +2 literally is the charge on the cobalt. We name the ligands first. The metal comes after it with its Roman numeral. And there's 6 of the waters, so it's hexa. And if you remember from the previous slide, water is aqua. So this thing is hexa aqua cobalt 2. It's the hexa aqua cobalt 2 ion, if you want to be official. All right, all one big word, no spaces. Water is called aqua. Hexa is the Greek prefix for 6. Hey, you've done your first coordination compounds nomenclature. All right, woohoo. Anyway, let's do another one. Now this crazy thing has a platinum, it has 2 ammonias, and 2 Cls, all right? So this one, we have 2 types of ligands. We have ammonia, which gets that weird amine name, and we also have 2 chlorides. Most of the normal monodentates, you replace the chloride by chloro. If you have a choice between amine or chloro to go first, you go at alphabetical. So this would be diamine, all right? And the other thing is that you'd then put dichloro. And the last thing you would do is put the platinum. But we need to figure out the charge on the platinum. Now, ammonia is neutral. Chlorides are -1, and there's 2 of them. This is going to be a platinum 2 center. And one thing I haven't talked about yet, but in this version of the molecule, notice how the chlorides, the green atoms, are 90 degrees from each other. This is a lot of times referred to as a cis form of this molecule. So the best name for this crazy thing, cis diamine dichloroplatinum 2. Okay, cis means that the chlorines are at 90 degrees. If they were 180 degrees across from each other, it would be trans. It's diamine with 2 M's because we have 2 ammonias, dichloro, 2 chlorines, and it's a platinum 2 center. So again, notice here how water is aqua and ammonia is amine with 2 M's, which is totally wild. Here's a molecule that we've bounced around a little bit. This is a copper. It's a copper 2+ because ammonia is neutral and 4 ammonias. So because NH3 is amine and 4 is tetra, you would say tetraamine copper 2 ion. All right, tetraamine 4 ammonias, copper +2, and this is an ion. It has a charge on it, so that's why we put the ion on it. All right. Now, most of the metals in this section are octahedral, but there are some tetrahedral, some square planar all over the place and stuff. So again, with crystal field theory, which we're not going to talk about in this class, unfortunately, you can do more predicting if it's tetrahedral or square planar, but for right now, we'll just go for it as is. This compound has a lot of atoms, and if you look at the structure, it's like, what? But if you look at the formula, all right, NH2C2H4NH2, that's the ethylene diamine thing. That's a bidentate ligand, and you'll notice that there are 3 of them, okay? So there's 3 ethylene diamines. It's a nickel +2, but ethylene diamine has a Greek prefix in the name. So if you have one of these kind of ligands where it has a Greek prefix in it, that's when you use the bis, tris, tetrakis alternate system. And 3 is a tris kind of version. So it goes bis, tris, tetrakis. So this would be the tris version. So you would write tris ethylene diamine, nickel 2 ion. Good to go. Notice how if you do use bis, tris, tetrakis, you do put the ligand in parentheses when you're naming it. And that makes it very clear that that whole thing you have in this case like 3 of them, etc., etc. Vasca made this compound. Everybody calls it Vasca's compound. Nobody calls it by its real name. What's wrong with them? Anyway, in this compound, we have a chloro, CO, which is carbon monoxide. If you remember, we call this carbonyl. And this crazy thing, it's triphenylphosphine. That's the name of that ligand. That's another kind of ligand in this particular molecule. Now up here you can see here's the carbon monoxide, here's the chlorine, and each of these purple atoms right there, they represent the phosphorus of the triphenylphosphine. Okay, so let's start off by putting these in alphabetical order. Carbonyl is before chloro, all right? Triphenylphosphine would be last, but triphenylphosphine has a Greek prefix, tri, in it. So for this one, we would also use the alternate system. It would be bis, parentheses, triphenylphosphine. And then finally, we have to think about what the charge is on the iridium. Well, triphenylphosphine is neutral, carbon monoxide is neutral, chloride has a -1 charge, and this compound is neutral. So that must be iridium 1. So this whole thing, carbonyl, chloro, bis, parentheses, triphenylphosphine, parentheses, iridium 1. You can probably see why everybody calls it Vasca's compound and not carbonyl, chloro, bis, triphenylphosphine, iridium 1. Oh my goodness, that's a long name. If you see a long name like that, break it down. All right, break it down into pieces that look familiar. So carbonyl, chloro, there's the word bis with that kind of thing, and then the metal with the ion. Good to go. Let's name this molecule NiNH32Cl2. All right, no problem. So when you do this, first of all, have to put the ligands in alphabetical order. We have amines and chloros, so amine comes first. Amine and chloro don't have Greek prefixes, so we'll just use di. It would be amine first, chlorine afterwards, so diamine dichloronickel, but we do need to figure out the charge on the nickel. Ammonia is neutral, chloride is -1, and there's 2 of them. This must be a nickel 2 center. So this thing would be diamine dichloronickel 2, and that would be the cool name of this compound. Woohoo! Again, if you see a long name like that, just break it down into little pieces, and then these molecules will absolutely fall for you. Here's just some more examples. This one right here, as you can see, a square brackets. This is the cation and this is the anion. So if this was, say, MgCl2, we would call it magnesium space chloride. Well, we're going to call the complex ion first, have a space, and then put chloride after it. So let's deal with the complex ion there first. It has 5 ammonias and a chloro, amine before chlorine. All right, so it would be pentaamine chloro. We do need the charge on the cobalt. Cobalt has a total of 3 chlorides that it's dealing with. So that is a neutral compound. That means that cobalt must be a +3. Remember that cobalt 3 is going to go at the end of the cation, and you'll have chloride after. So this crazy thing, pentaamine, 5 ammonias, chloro for the chlorine, cobalt 3, chloride. Notice that the hip chemist kind of has to figure out here, all right, well, there's 1 chlorine next to the cobalt, and there's now 2 chlorides outside the cobalt. It's a neutral compound, so that's how you can figure out how many Cls are there. This molecule has a cation and an anion as well, but notice here how the anion is the complex ion. So this compound is going to be potassium something, all right, where the something is the anion. So cyanide becomes cyano, and there's 4 of them. Tetracyano. It's a cadmium center, all right. Cadmium here, figuring out the charge is a little bit more complicated. Cyanide is -1, and there's 4 of them. And we have 2 +1 potassiums already, so that's a cadmium +2. But there's one more thing we need to do here. If the metal is in the anion, you change its name to an 8. So cadmium becomes a cadmate. This crazy thing, potassium space, because potassium is a cation, potassium tetracyano cadmate 2. Zinc becomes zincate, chromium becomes chromate, stuff like that. If you see that, that just means that the metal center is in the anion of the compound. Here's a compound. It's got a nickel, 2 chlorides, and 2 ethylene diamines. All right. Remember, the ethylene diamine has a Greek prefix in it, so we'll use the bis thing around it. Either way, chloro before ethylene diamine. 2 -1 chlorines means nickel's +2. This one's going to be dichloro bis parentheses ethylene diamine parentheses nickel 2. And finally, this one. This one's kind of near and dear to my heart. I used to make this compound in graduate school. It was the precursor for a lot of the chromium compounds I studied. That C4H8O thing is a compound called tetrahydrofuran. And I used to use THF, which we abbreviated as, all the time. So I put it in here just a little bit of nostalgia. Again, my apologies. Anyway, tetrahydrofuran has a Greek prefix in it. All right, so you can't call it tri-tetrahydrofuran. That sounds weird. You would use tris, in this case in parentheses, tetrahydrofuran. Chlorine is before tetrahydro alphabetically. This is a chromium +3. Tetrahydrofuran is neutral. So this would be trichlorotris tetrahydrofuran chromium 3. Used to be a beautiful purple color. I wish I had pictures and stuff. Alas, that's the way it goes. Kind of cool stuff. Let's name this molecule. Now this is an iron center with 5 carbon monoxides around it. And remember that if you have carbon monoxide, it's called carbonyl. So 5 carbonyls would be pentacarbonyl. But remember, carbon monoxide is a neutral atom. So that iron right there doesn't have a charge on it. So in this case, you would just call this pentacarbonyl iron 0. This is truly neutral iron. It doesn't have positive or negative charge on it. The COs actually kind of glue themselves to the outside. So pentacarbonyl iron 0, iron with a 0 charge. It has all of its electrons and protons. Cisplatinum is an example of a compound with the chlorines at 90 degrees. It's a platinum +2 center with a coordination number of 4. There's both a cis and a trans form. Trans would be 180 versus the 90 degrees we have right there. Cisplatinum is still being used as an anti-cancer drug. It's based on the platinol AQ, apparently, which is apparently still being used. Kind of cool. So, woohoo, go coordination compounds. Since we have a few more minutes, I want to talk briefly about isomers. Now in Chem 222, we did a lot with isomers when we drew out all the isomers of butane or pentane or something like that. Isomers literally are everywhere. And isomers, when you start putting inorganic metals inside them, become even more interesting. So I want to kind of re-look at isomers here a little bit and get you ready for future classes where you may see some of this stuff happen. Isomers are important not just in organic chemistry, but inorganic as well. And you can have different kinds of isomers. So like you can have cis and trans, or you can have many different kinds of variations, as we're going to see here in a little bit. If you have an isomer, it means you have the same number of atoms, but they're put together in a different way. And you can't just rotate one version into the other, basically. And I want to just briefly talk about these different isomer types here because they're really interesting, and you might see them either in organic chemistry or maybe inorganic later on. A coordination sphere isomer is a type of an isomer that just is wild. It depends, it really differs here as to what atoms are complexed to the transition metal, i.e. which ones are being Lewis bases and which ones are just anions to the metal center cation. And this is just weird to think about even to me. Now, these examples right here, all right, we've got a cobalt center, 5 ammonias, a chlorine, and a bromine. But notice here in the first one, chlorine is on the inside of the brackets and bromine's on the outside. And in the second one, bromine is on the inside of the brackets, chlorine's on the outside. The ones on the outside are like regular anions. And so you place one of these in water, and the anion, whatever it is, will just float away in the water, basically. So in this one, you'd have bromide float away, but in this one, you'd have chloride float away. Now you can probably imagine that even though chloride and bromide have -1 charges and they're halogens, there will be times where they will react differently. If you react silver nitrate with these, the silver nitrate will attack whatever is outside of the complex ion. So when bromide is outside and you add silver nitrate, silver and bromide make very insoluble compounds. You'll end up with AgBr solid. But on the other example, chloride was on the outside. The silver will attack the chloride. You'll end up with silver chloride instead of silver bromide. So notice in these cases that the Lewis base on the inside connected to the cobalt is a bit stronger. It's resisting the silver nitrate, at least under these conditions. This is an example of a coordination sphere isomer. They're not super common, but they do pop up once in a while. Same formula, but if the anion is a Lewis base, or truly the anion, it can make a big difference. Linkage isomers, I still, to a point, just have a problem believing that they're real, but apparently they are. These two examples here are cobalt centers with 5 ammonias each, but the nitro is connecting to the metal center in different places. In the first one on the left, the yellow-colored solid, the nitro is connecting at the nitrogen, and the second one, the more red one, the nitro is connecting at the oxygen. They call the ones where the nitro is connecting pointing at the oxygen, the nitrito, and if it's a regular NO2 group, it's nitro. And you do have different kinds of reactivities, all right? In the second one there, the red-orange one, red color one, the nitrogen's running around. It could be a Lewis base to something. So you do see different kinds of reactivities. I kind of still don't always believe that these are real. It just seems like, oh yeah, your stuff just oxidized. Oxidation usually will turn the color of your complex a little different color. But there's been enough studies on it and stuff that it does seem to be real. My hat's off to these scientists. It does show a different kind of isomer than people usually see. Geometric isomers is really what we dealt with a little bit anyway back in Chem 222. And classic geometric isomers include things like cis and trans, all right, different combinations. And this also arguably would incorporate like isomers of pentane or something like that. But in this section, what I want to do is I want to talk more about cis and trans a little bit for inorganic complexes, and also talk about what's called mer and fac, and that's another kind of a isomer you'll see when it comes to metals. Like cis and trans in organic chemistry, cis and trans can lead to compounds with different colors, melting points, reactivities, polarities, all that kind of stuff. So it's pretty crazy and stuff then to think about all the possibilities that exist when it comes to chemistry. Here's the cis version, that's cis platinum. That's the one on the left. And there is a trans platinum kind of version on the right. And you can see that cis and trans in our inorganic chemistry comes down to 90-degree angles or 180-degree angles when you have a square planar complex. And that's kind of cool. The trans one would be less polar, definitely, than the cis polar. So it makes, or more, the cis one would be more polar and the trans would be less polar, definitely. So it can make a big difference. You can also have octahedral cis and trans. Octahedral cis means that the two atoms that are alike are 90 degrees, and octahedral trans means that the atoms are 180 degrees. So again, trans should be less polar, cis should be more polar. You can see some pretty drastic differences when it comes to these molecules. Mer and fac are new players on the block, and mer and fac happen when you have three atoms that are the same around an octahedral center. So both these molecules listed here, there's a dark blue central atom, there's three light blue atoms, and three yellow atoms. If you look at the left one, the mer version, which comes from meridional apparently, two of the atoms, two sets of atoms, are 180 degrees the same. So if you look at this one right here, the top atom and the bottom atom, those are both blue, all right, and they don't change. And in the rotation part of the meridional, you also have a yellow opposite a yellow molecule right there. So mer isomers are certainly less polar than the fac, and fac comes from facial apparently. All of the bond angles in a fac isomer are 90 degrees. You don't have any 180 degrees blue metal blue bonds or yellow blue metal bonds. All of the angles in the facial isomer are 90 degrees. So because again there's differences in polarity, mer and fac can come in really handy. Fac is facial, and there is kind of like a triangle of atoms when you have a facial isomer that are all the same. There's like a blue triangle on kind of the top, and there's a yellow triangle, if you will, kind of opposite on the bottom. Meridional, though, has that 180 degree orientation, which makes it a little easier sometimes to see. The wildest kind of isomer, though, that we haven't talked about yet, but you'll probably talk about in organic chemistry if you take it, is when you get to what's called optical isomers. And these are wild. Now, before I start talking about this slide, I want you to look at your two hands, all right? You have a right hand and you have a left hand. And the right hand and the left hand both have a thumb, and they have a pinky, and they got the finger to flip somebody off if they cut you off on the freeway. No, seriously, you can use it for looking up dictionary entries, whatever. Okay, they're the same kind of fingers, but they're not the same, all right? Like, it's almost like if you put your right and your left hand together, they're like mirror images of each other, all right? But if you try to put the right hand in front of the left hand, well, that's not going to happen. Either it goes palm to palm, or the other sides are opposite and stuff like that. So your hands are example of what's called a chiral isomer. And if you have this handed type of isomer where it's like a mirror image, this leads to what's called enantiomers. So your hands are considered chiral because if you look in the mirror, it's like one is opposite the other. The right hand and the left hand would both be called enantiomers. And enantiomers are great about bending light. So they call them optical isomers because the light will actually bend a little bit from them. Substances can be chiral, have the handed nature, if they don't have a plane of symmetry. So for example, your hands don't really have a line that goes through them or anything like that. I want to talk about down here in these examples, isomer 1 and isomer 2, they all have a black central atom, and they have a white atom, a blue atom, a pink atom, and kind of a yellow atom around them, okay? So let's put isomer 2 and isomer 1 together, and let's pretend that we have a piece of glass or something like that. Notice how they kind of look like they're mirror images of each other, like blue to blue, yellow to yellow, whites on top, pinks in the back. They look like your hands when you put them next to each other. But isomer 1 and isomer 2, you can't rotate one into the other, all right? They're just like your hands. They look like they're mirror images of each other, but you can't rotate one into the other. So molecules with like carbon in the middle and 4 types of atoms around it, those are going to be chiral. You're going to have at least 2 enantiomers that can do different things. They'll bend light different. This is an area that kind of blew chemists' minds until about the 50s or so. In the 50s and 60s, they developed technology to identify different isomers if they were chiral. And that was no small feat. And for a long time, people really didn't understand what this was all about. Here's a picture showing again like your hands, all right? If you put your one hand, your left hand up to the mirror, it looks like the right hand is in the mirror opposite you, or you can just put your 2 hands together, that's fine. This shows that you have a chiral system, and each hand would be considered an enantiomer. Enantiomers will bend light a little bit, and that's what makes them kind of interesting. Now in the lower right is a cheesy example of a molecule that is also chiral looking at itself in the mirror, and you can see that they're kind of mirror images of each other. But if you were to physically take the molecules and put them together, you could align 2 of the atoms together, but the other 2 would be opposite. So you're not going to be able to superimpose one of those molecules on the other, just like you can't superimpose your hands on top of each other. These crazy optical isomers do some wild things. They possess a lot of identical properties. So for example, solubilities are similar, their melting point and boiling points are similar, usually their colors are the same, they will oftentimes have similar reactivity. But if you have an enantiomer and you react it with another chiral agent, you're going to see differences in reactivity. So the first way that they figured out that enantiomers exist is they use what's called plane polarized light. And plane polarized light is like light in just like one type of direction. And they will actually have different properties depending on if you have the one enantiomer or the other. Now, to get plane polarized light, you start with regular light, which comes out 360, all different degrees, and you use a polarizing filter, and that basically isolates the light along a plane, so an up and down plane in this example, but you don't have the left and the right or anything like that parts. It's not too hard, apparently, to make plane polarized light, and plane polarized light will sometimes be able to separate or figure out that you have enantiomers, and sometimes you can use that to figure out how to separate them. They use a lot of terms in enantiomers and chiral systems. They use what's called dextrorotatory and levoratory, and those get the symbols D and L. D means dextrorotatory, it means that the light is rotated to the right, and levoratory, which is left, means that light is rotated to the left. So if you have an enantiomer, only the left hand or only the right hand, you will see the light rotated to the left or the right. It's pretty cool. This is a way they can detect if you have enantiomers. But the problem with this is that a lot of times when you're making these, you'll end up with just as much left-handed stuff as right-handed stuff. They call those racemic mixtures. And your plane polarized light going through racemic mixtures, nothing's going to happen because you have just as much rotation to the left as you have to the right. It's really hard sometimes to tell that you have an enantiomer. You have to separate them out. If you want to separate out enantiomers from each other, i.e. get the left hands away from the right hands, you can use a chiral reagent. And a chiral reagent, i.e. only left or right hand, will sometimes be able to pull one enantiomer away from the other. Here's an example of this. Let's say that we have a racemic mixture of this cobalt compound. Now this cobalt actually has both D and L. This is a chiral system, and initially we have a racemic mixture, which means we have just as much left hand as right hand enantiomer, or just as much D as L. Now, you can take this chiral reagent, and these are not cheap, by the way, they're very difficult to make. This chiral reagent has the D form, and the D form of the chiral reagent only reacts with the D form in the racemic mixture. So down here, this is the cobalt complex again, but now it's got the it's got the D enantiomer, that D chiral reagent acting with it. The other one, the L version, just reacts with chloride and goes its own way. It doesn't do anything. So using a chiral reagent, sometimes you can pull the left and right hands one away from the other, which is not easy. Then you would have a pure enantiomer. You could put the plane polarized light through it and see it go left or right a little bit. It's pretty cool. This is a really interesting area of chemistry, and you have to be very detail oriented. Make sure you have the right enantiomer, stuff like that, the right reagent to react with. It can be very complicated, but the effects are also super important. The procedures that are used, again, are complex, but I can't emphasize enough how important it is. I want to talk very quickly about Ritalin and thalidomide. Now, thalidomide was a drug that was approved in certain European countries around the time of the 1950s, and it was supposed to help women when they give birth and stuff like that. It was supposed to be really good. Unfortunately, thalidomide was a product that had both a D and an L form, all right? There were two enantiomers, two hands in the form they sold to pregnant women, all right? Well, the one form of thalidomide was wonderful, and it did everything it was supposed to do. But the other form was really bad, and the children born had lots of birth defects and stuff like that. Really, really sad. There was a huge lawsuit that happened for many decades, as I understand, in England, and finally the victims got paid money for this and stuff, which is really crazy. It was never approved in the United States for use, but you will see sometimes old ads for thalidomide and stuff. Pretty crazy. Now, Ritalin is one you're hopefully aware of. It's used for kids that have attention deficit disorder. It supposedly makes them more mellow. Well, apparently Ritalin has a left and a right hand side enantiomer as well. It has a D and an L. And the one enantiomer is the good one. It helps the kids. But the other one apparently causes lots of problems and stuff. So be aware that these kind of things are very important when it comes to pharmaceuticals. If you don't have the right enantiomer, you could have really bad reactions. And finally, I couldn't help but resist and put up Samuel L. Jackson, which is his real name, and also Samuel D. Jackson, because D and L are the two enantiomers, and you can see they're looking the opposite way. Oh, my sense of humor. That's it for chapter 19. Thank you for spending time with me. Thank you for watching these videos. I really do appreciate it. Hopefully this has given you a good idea of the things that transition metals offer, and it'll also help you with complex ion nomenclature and stuff like that. I do have a study guide, which is a bulleted list of the highlights from this area, and then following this slide, you'll see some important equations from this area, and also have some end of chapter problems. And most of the chapter problems are going to be on nomenclature at this point. Also Also in the printed notes, there will be some information on crystal field theory and how it can relate to molecular orbital theory. It's really cool. It helps you explain colors and stuff like that, but I just don't have time to talk about it right now. Sorry, maybe one day in the future. All right, if you have questions on any of this, please reach out to me or the Learning Success Center /Avid Center. We're happy to help you out. Thank you again for spending your time with me. Good luck with your studying and have a wonderful day.